So we're going to talk about accuracy assessment. So what is this and why do we care? How do we need to gather ground data or sampling schemes? We'll just talk about briefly. What is acceptable data? And then we'll spend most of the time unpacking this confusion matrix, which is a way to quantitatively actually display your accuracy. So what you're seeing here is an example of arduously collected validation data. And so this is like a total, I think, of 2,304 trees that were collected through some combination of gathering them using Google Earth, identifying, not Google Earth, Google Street View, identifying trees, actually just looking at them through the computer, but close up. All these green things are field plots that we actually went out and visited in person and measured and identified all the trees. And then all of these trees are ones at a park that we did an even more kind of rigorous assessment of their health and structure. So it took a long time to gather all this data, but then it was a nice way to evaluate the accuracy of my tree species classifier. So as I kind of said already in class, why do we care? Well, it's easy to produce good looking maps and kind of wave our hands at whether they are accurate or not. But we definitely don't want to ignore the actual accuracy assessment, even though it's a little bit difficult. As I just said, going out in the field or, having some, it's a very manual process regardless of how you do it. So you want to bring in some other source of information that's better than the data that you're using in your automated classifier. So for instance, if we're looking at Landsat data that's 30-meter resolution, validation data could plausibly be Google Earth imagery. If you're just trying to say, is this a building? Is this a tree? Is this road? Or other stuff that you can assess visually from above at much higher spatial resolution. So, over here, which of these maps is more accurate? It's tough to say just by looking at it. And furthermore, we don't really know what the classes are. But I did do an accuracy assessment, I think, on a 4 or 5 class map. And it was the one on the bottom, which did a better job. So who knew? But it's nice to have a number. So our key steps are select how we want to sample the ground data, the actual validation data. Today in the Iowa example, I just kind of randomly distributed points, but it had a bias to it because I was selecting points that were most likely productive fields, for example. Get the reference data, either by visiting in person or some other trustworthy source. Create your error or confusion matrix and analysis and see how you did. If you did poorly, go back and start the whole process over again. And really, the process that would be starting over again would be the actual classification. So we won't dig into this too much, but it is important to reduce kind of bias and include the full range of spectral variability of your class to have a good sampling strategy for both a training and a validation data set. So, some ways to do this are to say in your scene in Iowa or in DC, just say have ArcGIS or something spray a bunch of random points around your study area, and then maybe using Google Earth, you actually go in visually and identify what each of those points is. And so this is a good way to make sure you're accounting for the main land cover classes and you're doing it in an unbiased way. But the disadvantage is that it may undersample small but possibly important classes. So in the boreal forest, for example, the Forest Service wants to classify the tree species, most of which are black spruce, white spruce, and birch, but they are also interested in aspen, which only represents 5% of the total tree cover. And so a random sampling scheme for validation wouldn't get enough Aspen in there to know if we're doing well at classifying Aspen. So there's other ways to get at that better. Systematic is not the answer to that, not the answer to the way to get Aspen sampling better, but it is a useful strategy to just lay out a grid of points and you're sampling systematically. And we're not really going to worry about this disadvantage of periodicity. That's kind of rare and not necessary to consider right now. Stratified random sampling. Now, this probably is the good way to figure out if you're doing a good job with Aspen or not. Basically, we're saying we're going to identify on the ground or from Google Earth imagery or something, 50 black spruce trees, 50 white spruce, 50 birch, and 50 aspen. And so you can see that there's an equal number of each of these, even though that there's far more of these three species in the forest than this one. But so this is basically a stratified sampling strategy in order to make sure that your classifier works well for these rare classes. Finally, cluster sampling, not ideal, but sometimes pragmatically necessary. And so this is exactly what I pointed out in this first slide. These green plots right here, they are cluster samples because we measured and identified every tree that exists in those plots. And that's just because it would be far too difficult to do field work without doing something like that. But it's not completely random by any stretch. There we go. So actually gathering your training and validation data, how much data do you need to get? Well, partly it depends on how much within class spectral heterogeneity. Probably if you gathered 5 ocean points in Santa Barbara area in the Pacific Ocean, that would probably be fine because it has low within class spectral heterogeneity in water. But if you're talking about a dense urban class, well, there's a lot of spectral heterogeneity in that class. So you probably need a bunch more points to do a good job. Now, I realize a bunch is not well defined, but it just depends on the application. And so we frequently start at like 30 or ideally 50 plus pixels per class as a starting point to see how well that works. Then, you do some examinations of the class histograms band by band, and you start to see if that's adequate. So as I said, different ways to gather validation data, field measurements, these virtual visits that I was talking about in my project, where I can look at this tree and I can say, oh yeah, it's a Ficus microcarpa. Great, good to go. So it's a little depressing way to do field work because you still don't leave your office, but it was effective and efficient. Or high resolution imagery is a pretty common one. So, the Landsat pixels may be something like this size, but you can clearly see some of the things that you might want to know about land cover classes in here. So you can identify tree canopy, if not tree species. You can identify buildings, impervious ground, and grass is maybe somewhere in here. So it just depends on kind of the specificity of the classes that you're trying to identify. Okay, so that's gathering the data. And so, now you've done this classifier in ENVI with your validation data set, and you want to see how well you did. So in this case, we are going to be classifying residential, commercial, wetland, forest, and water. And we want to know which ones of those classes got confused with which other ones of those classes. And by using that word confusion, that's where we get this idea of a confusion matrix. So the rows are the what you actually did, what each pixel in your validation data set actually got classified as. The columns is your ground reference information, so what things actually should be. And so in this case, it's easiest to think of is if everything here should have been residential. And then you kind of go down the list and you see what the algorithm actually classified that particular pixel as. You get down to the bottom and this should equal your actual validation sample size for that class. And so it's a good check to see, oh, did I click on 73 residential pixels? Okay, yes, then I'm looking at my reference information right there. And so the idea is you want high numbers along this diagonal because that is where residential meets residential. And so anything that's in that box is correctly classified. Commercial is commercial, wetland, wetland, forest, forest, water, water. So before we go into the more interesting products that you can derive from this confusion matrix, let's just look at the overall accuracy that you can get from this. Let's see what that is. Okay. So we're going to look at the overall accuracy. Then we'll look at accuracies for each class. So this will be called omission and commission error. And finally, we'll look at the kappa estimate, which I'll explain in a minute. So let's look at overall accuracy first, because this is the easiest one and the first thing that most people report. So I said the correctly classified pixels are all in the diagonal. And so basically the overall accuracy is just the sum of the correctly classified pixels over the total number of reference pixels. So you're just summing everything along the diagonal. And so you're seeing that right here. So the sum of the diagonals divided by the grand total. So if you add all of these together, you get 407. And so this total divided by 407 gives you this overall accuracy of 94%. So that's good. You know, that's nice overall. You know, that's a good result. 94% is a nice number, but it doesn't really tell you the whole story. So for example, one thing to note here is they've got more water reference classes than reference pixels than any other class. And water is super easy to classify well, and it also may not be as super important for their study area. So they may be inflating their accuracy, their overall accuracy, because they have so many water pixels. And they may care more about forest, but they don't have as many forest reference pixels. They only had 50. So we want to kind of dig deeper to see you know, what the difference is among the accuracies per class. So the first thing we'll look at is producer's accuracy, which is the inverse of omission error. So, okay, what percent of validation pixels in each class did we miss, aka omit, in our classification? So let's start with that, and then we'll come back to producer's accuracy. So we can see here that we got 70 out of 73 correct, but we missed 3. We should have gotten 3 more pixels assigned to residential, but instead we classified that as commercial. So our omission error, just in terms of pixels, is just 3 out of 70. The producer's accuracy is just the inverse of that, basically, or we flip that around. It's a little more, the terminology becomes a little archaic, kind of these old cartographic terms. But basically, producer's accuracy is just because the producer of the classification is interested in how well a certain area can be classified. We don't want to miss anything as a producer. So it's just going to be the value in the diagonal over the column total. And the value in the diagonal is 70, and the column total is 73. And so it doesn't matter what we're calling it, really, but it is an important number. This 70 over 73 is 96% producer's accuracy, and 100% minus producer's accuracy equals omission error of 4%. So 4% omission error for the residential class. So we would then, we could do that down the line here. We could say, okay, what is the deal for wetland? Well, we could say 99 were correct out of 103 total. And so 99 over 103 equals producer's accuracy. So it's pretty simple. And then we would know, how well we mapped wetland. But that only gives us one piece of the puzzle, because if you just say that everything is wetland, then you'll get 100% producer's accuracy for wetland, but you'll be way over mapping wetland. There'll be way too much wetland mapped. And so this is where we have to deal with user's accuracy, or commission error. Commission means, instead of omitting, you're adding additional pixels that you shouldn't be adding to a given class. So in this case, we look across the rows and we say, okay, 70 residential were still correct, but what else did residential map? So, if we kind of flip this around, we say commercial missed 5 pixels that were mapped as residential. So the bigger these numbers are, it means kind of the more crazy over mapping the residential class can become, which is a problem in its own right. So how much commission error is here? Well, this is just going to be then 70 over 88 is going to give you that user's accuracy. And so, sorry, let me quickly define this. The probability that the location that a user places their finger randomly on a map is accurately classified. So I'm kind of putting those definitions out there, but I don't put much stock in the actual terminology themselves. We just say, okay, we know it when we see it. We say user's accuracy is 70 over 88 is 80%. So the higher this number is, the less overmapping that class did. So if you had a producer's accuracy of, again, 100% and a user's accuracy of 30% for forest class, that meant that way too many pixels on this map were actually mapped as forest. And the opposite, of course, 100% means you missed a lot of forest and you didn't map anything else as forest that shouldn't be mapped as forest. So we kind of, we want both of these to be high and ideally at least balance them more or less. So in the same thing as producers and omission, users and commission are just the reciprocal of one another. So, 100% minus that 80% user's accuracy equals this 20% commission error. Okay, so people like to report these tables like this for every class because it gives a more fair assessment. If we cared about the Aspen class, for example, we wouldn't really care as much about overall accuracy of a land cover map. It might be awesome, but we still might have not mapped Aspen properly at all. So we look down at these statistics and we can say, okay, well, we did a great job of mapping black spruce, but we did a terrible job of actually mapping Aspen. So we may need to go back to the drawing board to figure out a better classifier. So the final standard report out that you can derive from the confusion matrix is this kappa coefficient of agreement. And looks a little gnarly as an equation, but it's an important one, and it's really not that hard to calculate. It's basically the idea is that computing an overall accuracy, a bit of your accuracy can be really just based on chance. So if you are just classifying forest versus water, you should be able to get 50% accuracy just by flipping a coin and assigning each pixel to forest or water, because there's only two classes. So the fact that you train a max likelihood classifier and get 60% accuracy doesn't really mean you're anything that special. It just means you're 10% better than what would happen with random chance alone. So Kappa gives you this skill metric to say, how much better are you than random chance? By you, I mean the algorithm, really, or your classification workflow. How much better are you than random chance? So the more classes that you have, the closer the Kappa number comes to overall accuracy, because you couldn't do that well with classifying 40 classes by random chance. So most of your accuracy would therefore come from actual skill or information or algorithmic, efficiency. So to actually measure this, we want to look at the observed accuracy. So that's really what you see in the diagonals, minus chance agreement over 100% accuracy minus chance agreement. So, it's this difference between observed and chance that gets you at what is your skill in making this classifier. So let's break this down a little bit. Break down this kind of hairy looking equation. So first of all, what do we need? We need just the n, the total of all of your reference information is going to be your n. So that's an easy start. You need to know how many observations you have. The next term here is the sum. So the sum from 1 to the number of classes. So 1 to k is the number of classes of what you did correctly. So this is your observed accuracy. So in this case, k equals 3 because we only have forest, road, and grass. And so we are just adding together the things we did correctly. So 20, 28, and 17. The next term is going to be our chance term. So we don't need to dig into the reasons for why this is a chance agreement term, but from a pragmatic standpoint, it's all we're doing here is doing multiplication of the column totals and the row totals. And so over here, you've got the row totals times the corresponding column total. And then you're summing all of those products. And so we start with forest column times forest row plus road column times road row times grass column times grass row. And you can see this term just boils down to this. So it's something that is simple once you set up an Excel spreadsheet to help you do this automatically. So that's pretty much it, because on the bottom we just have n squared, and so that's just going to be 77 squared, and this is also the exact same as this. So there's nothing new to know. And so when you turn the crank and run this through your Excel spreadsheet, you get an overall accuracy of 84%, remember, just based on the sum of the diagonals divided by 77. But there's only 3 classes, so you don't get all the credit for doing an okay job in this classifier. And that's expressed by this kappa that's somewhat lower. So kappa is always expressed as a fraction. And so it's fairly comparable to the overall accuracy, but you express it differently. And you kind of just think about it as, how much lower is that kappa than the overall accuracy? And it's dependent on 2 things. It's dependent on how good you are at the classification and how many classes there are, more or less. That's it.